The Earth and the Moon share an extraordinary relationship. This bond is not merely one of proximity, but of profound interconnectedness. The Moon, Earth's only natural satellite, orbits around our planet in a dance that has lasted billions of years. This enduring companionship is visible in the night sky, a constant reminder of the cosmic connection we share with our nearest celestial neighbour. The Moon's presence influences many aspects of life on Earth. It has guided ancient civilizations in their calendars and agricultural practices. Even today, the Moon continues to inspire wonder and exploration. From the gentle pull of its gravity to the way it lights up our night, the Moon is a vital part of Earth's natural rhythm. But beyond its beauty, the Moon plays critical roles in Earth's geophysical and environmental dynamics. It affects our oceans, our weather, and even the stability of Earth's tilt. This introductory section sets the stage for a deeper exploration of how the Moon shapes life on our planet and the history of our quest to understand it. In the following sections, we will delve into the Moon's influence on Earth's tides and stability, revisit the monumental Apollo missions, and look ahead to future lunar explorations. We will also explore the mysteries of the Moon's surface and what lies beneath, as well as the science of eclipses and the Moon's origins. Finally, we will consider the broader implications of this cosmic relationship for future space exploration. The Moon's gravitational pull is the primary force behind Earth's ocean tides. As the Moon orbits our planet, its gravity exerts a pulling force on Earth's waters. This creates bulges in the oceans, known as high tides, on the side facing the Moon and the side opposite. In between these bulges, we experience low tides. This rhythmic ebb and flow of the tides are crucial for many coastal ecosystems. Marine life, such as crabs and certain fish, rely on tidal patterns for breeding and feeding. But the Moon's influence extends beyond the tides. It also plays a significant role in stabilizing Earth's axial tilt. The Earth tilts at an angle of about 23.5 degrees relative to its orbit around the Sun. This tilt is responsible for our seasons. Without the Moon's stabilizing influence, Earth's tilt could vary wildly, leading to extreme climate changes. Such fluctuations would make our planet a much less hospitable place for life as we know it. Moreover, the Moon's gravitational interaction with Earth gradually slows our planet's rotation. This phenomenon, known as tidal braking, results in the lengthening of our days over geological time. Millions of years ago, a day on Earth was much shorter, and this gradual deceleration continues to influence Earth's rotation. In summary, the Moon is not just a passive companion in the night sky. Its gravitational influence is vital for maintaining the delicate balance of Earth's environmental systems. From regulating tides to stabilizing the planet's axial tilt and rotation, the Moon's presence ensures the continuity of life-sustaining conditions on Earth. As we move forward, we will explore humanity's efforts to reach and understand this celestial body through the history of lunar exploration. The Apollo missions represent a pinnacle of human achievement and curiosity. Initiated by NASA in the 1960s, these missions aimed to land a man on the Moon and bring him safely back to Earth. This goal was famously articulated by President John F. Kennedy in his 1961 speech, setting the stage for what would become one of the most defining moments in space exploration. Apollo 11, the first successful manned mission to the Moon, launched on July 16, 1969. Astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins embarked on this historic journey. On July 20, 1969, Armstrong and Aldrin became the first humans to set foot on the lunar surface, with Armstrong's iconic words, "That's one small step for man, one giant leap for mankind," resonating around the world. They spent over 2 hours exploring the Moon, conducting experiments and collecting samples. Subsequent Apollo missions built on this success. Apollo 12, 14, 15, 16 and 17 each brought new discoveries and technological advancements. Apollo 15, for instance, introduced the Lunar roving vehicle, allowing astronauts to travel further and conduct more extensive scientific research. These missions provided invaluable data on the Moon's geology, environment, and potential resources. The Apollo missions also had profound cultural and political impacts. They demonstrated the capabilities of human ingenuity and international cooperation. The sight of Earth from the Moon, a fragile blue marble in the vastness of space, sparked a new perspective on our planet and the importance of its preservation. It was a moment that united humanity in awe and wonder. In conclusion, the Apollo missions not only achieved their primary goal of lunar exploration, but also laid the groundwork for future space endeavors. They expanded our understanding of the Moon and inspired generations of scientists, engineers, and dreamers. As we look ahead to new lunar missions, we continue to build on the legacy of those pioneering explorations. The 21st century has ushered in a new era of lunar exploration. Countries around the world are gearing up for missions to the Moon, driven by advancements in technology and a renewed interest in space. NASA's Artemis program aims to return humans to the Moon by the mid-2020s. Named after Apollo's twin sister, Artemis seeks to establish a sustainable human presence on the Moon, paving the way for future missions to Mars. The Artemis program plans to land the first woman and the next man on the lunar surface. It will also establish the Lunar Gateway, an orbiting outpost that will serve as a staging point for deeper space exploration. The Gateway will support long-term lunar missions and scientific research, enabling astronauts to stay on the Moon for extended periods. In addition to NASA, other space agencies and private companies are joining the new space race. The European Space Agency, ESA, is collaborating on the Artemis program, while China has ambitious plans with its Chang'e missions. The Chang'e 4 mission, for example, successfully landed on the far side of the Moon in 2019, a first in lunar exploration. China aims to establish a robotic research station on the Moon by the 2030s. Private companies like SpaceX and Blue Origin are also key players. SpaceX's Starship aims to transport humans and cargo to the Moon with the goal of making space travel more accessible and affordable. Blue Origin's Blue Moon lander is designed for cargo missions and human exploration, supporting NASA's Artemis program. This new wave of lunar missions signifies a collective effort to expand human presence beyond Earth. By building on the legacy of the Apollo missions, we are poised to unlock new scientific discoveries and technological advancements. The Moon serves as a stepping stone for future exploration of Mars and beyond, marking an exciting chapter in our journey to the stars. The Moon's surface is a landscape of both wonder and mystery. It is marked by vast plains, towering mountains, and deep craters. These features tell the story of the Moon's turbulent history, shaped by volcanic activity and impacts from space debris. The most notable of these are the lunar maria, which are large, dark basaltic plains formed by ancient volcanic eruptions. These maria cover about 16% of the Moon's surface and are primarily located on the near side. One of the most intriguing surface features is the South Pole Aitken Basin. Located on the far side, this massive impact crater is one of the largest in the solar system. It stretches about 2,500 kilometers in diameter and reaches depths of up to 8 kilometers. Studying this basin can provide insights into the Moon's internal structure and the history of impacts in the early solar system. Another mystery is the distribution of water ice on the Moon. Recent missions have confirmed the presence of water ice in permanently shadowed craters at the poles. These regions, which never receive sunlight, have temperatures cold enough to trap water molecules. This discovery has significant implications for future lunar missions, as water can be used for drinking, fuel production, and other essential resources. The Moon's surface is also home to unusual geological formations known as lunar swirls. These bright, swirling patterns are found in some regions and are associated with magnetic anomalies. Their exact formation process remains a topic of scientific debate, with theories ranging from cometary impacts to interactions with the solar wind. In summary, the Moon's surface is a testament to its dynamic history. Each crater, mountain, and plain holds clues to the processes that have shaped our celestial neighbor. As we continue to explore and study the Moon, we uncover new mysteries and deepen our understanding of its complex geology. Section 6. The moon's subsurface. What lies beneath? Beneath the moon's surface lies a hidden world waiting to be explored. The subsurface composition and structure provide key insights into the moon's formation and evolutionary history. Lunar missions have revealed that the moon is composed of distinct layers, the crust, mantle and core, similar to Earth but with notable differences. The lunar crust, the outermost layer, is composed primarily of silicate minerals. It varies in thickness, averaging about 50 kilometers on the near side and up to 100 kilometers on the far side. This asymmetry is believed to be the result of differences in the thermal history and impact events. The crust is also rich in anorthosite, a type of rock that gives the highlands their bright appearance. Beneath the crust lies the mantle, which extends down to the core. The mantle is composed of minerals such as olivine and pyroxene and is believed to be the source of the basaltic lava that formed the Lunar Maria. The mantle's composition and the presence of certain elements can provide clues about the moon's thermal evolution and volcanic activity. The core of the moon is much smaller compared to Earth's core, with a radius of about 350 kilometers. It is composed of metallic iron with some sulfur and nickel. The core is partially molten, which has implications for the moon's magnetic field. Understanding the core's properties helps scientists learn about the moon's magnetic history and its current geodynamic state. In addition to these layers, the moon's subsurface contains valuable resources. Helium-3, a rare isotope, is more abundant on the moon than on Earth and has potential uses in future fusion energy production. The presence of water ice in the subsurface also offers practical benefits for sustaining human presence and supporting long-term lunar missions. In conclusion, the moon's subsurface holds many secrets that can enhance our understanding of planetary formation and evolution. Continued exploration and study will unlock these mysteries, providing a deeper knowledge of our celestial companion and its potential resources. Section 7. The science behind eclipses. Eclipses are among the most awe-inspiring celestial events, and the moon plays a central role in both solar and lunar eclipses. A solar eclipse occurs when the moon passes between Earth and the sun, casting a shadow on Earth. This can only happen during a new moon when the sun, moon and Earth are aligned. Depending on their alignment, solar eclipses can be total, partial or annular. In a total solar eclipse, the moon completely covers the sun, allowing observers in the path of totality to experience a brief period of darkness during daytime. This phenomenon reveals the sun's outer atmosphere, the corona, which is usually hidden by the sun's bright light. Partial solar eclipses occur when only a part of the sun is obscured by the moon, while annular eclipses happen when the moon is too far from Earth to completely cover the sun, leaving a ring of sunlight visible. Lunar eclipses, on the other hand, occur when Earth passes between the sun and the moon, casting its shadow on the moon. This can only happen during a full moon. There are 3 types of lunar eclipses: total, partial and penumbral. In a total lunar eclipse, the entire moon falls within Earth's umbra, the darkest part of its shadow, giving the moon a reddish hue known as a blood moon. This coloration is caused by Earth's atmosphere bending and filtering sunlight, scattering shorter wavelengths and allowing the longer red wavelengths to reach the moon. Partial lunar eclipses occur when only a portion of the moon enters Earth's umbra, while penumbral eclipses involve the moon passing through Earth's penumbra, the outer part of its shadow, causing a subtle shading on the lunar surface. Eclipses have fascinated humans for millennia, inspiring myths, scientific inquiry and cultural tradition. Understanding the mechanics of eclipses not only deepens our appreciation for these events, but also enhances our knowledge of celestial dynamics and the intricate balance between the Earth, Moon and Sun. Section 8. The Moon's origins, theories and evidence. The origin of the Moon has intrigued scientists for centuries. Several theories have been proposed to explain how this celestial body came to be. The most widely accepted hypothesis is the giant impact theory. According to this theory, the Moon formed from the debris left over after a Mars-sized body, often referred to as Theia, collided with the early Earth about 4.5 billion years ago. The giant impact theory is supported by several lines of evidence. The composition of lunar rocks brought back by the Apollo missions is similar to that of Earth's mantle, suggesting a common origin. Additionally, the isotopic similarities between Earth and Moon materials indicate that they formed from the same primordial matter. Computer simulations of the impact scenario also show that such a collision could result in the formation of a Moon-sized satellite. Other theories have been proposed, including the co-formation theory, which suggests that the Earth and Moon formed together as a double system from the primordial accretion disk. However, this theory struggles to explain the compositional similarities and differences observed between the two bodies. The capture theory posits that the Moon formed elsewhere in the solar system and was captured by Earth's gravity. While this could account for certain aspects of the Moon's orbit, it fails to explain the isotopic similarities. Another intriguing idea is the fission theory, which suggests that the Moon was once part of Earth and was separated due to the planet's rapid rotation. This theory, however, does not adequately account for the angular momentum and energy required for such a process. Ongoing research and future lunar missions aim to refine our understanding of the Moon's origins. By studying the Moon's composition, structure, and the dynamics of its orbit, scientists hope to uncover more details about the early solar system and the processes that led to the formation of our closest celestial neighbor. Section 9. The significance of Earth's relationship with the Moon. The relationship between Earth and the Moon is a cosmic connection that has shaped the history and future of our planet. From influencing tides and stabilizing our climate to inspiring human exploration and scientific discovery, the Moon's role is indispensable. This connection has driven humanity to look up, dream, and reach for the stars. The Apollo missions were a testament to human ingenuity and the desire to explore the unknown. They marked the beginning of a new era in space exploration, one that continues to evolve with the Artemis program and international collaborations. The prospect of establishing a lunar base opens up new possibilities for scientific research and the potential for deeper space missions. Understanding the Moon's surface and subsurface, as well as its origins, provides insights into the history of our solar system. The study of eclipses and the Moon's gravitational influence helps us comprehend the dynamic interplay between celestial bodies. Each discovery adds to our collective knowledge and brings us closer to unraveling the mysteries of the universe. The Moon also holds practical significance for future space endeavors. Its resources, such as water, ice, and helium-3, could support long-term human presence and sustainable exploration. Establishing a lunar base would serve as a stepping stone for missions to Mars and beyond, expanding our horizons and pushing the boundaries of human capability. In conclusion, the Earth-Moon relationship is a cornerstone of our understanding of the cosmos. It has shaped our past, influences our present, and will undoubtedly play a crucial role in our future. As we continue to explore and learn from our celestial neighbor, we are reminded of the profound interconnectedness of the universe and our place within it.